the rebound on black bars is super brutal. Look at that.
He's just
He's bouncing to that. Like, no,
All right, how's everyone's weekend? Yay. Good stuff. All right, so questions. ODP questions first. Any ODP issues? Does 204 make sense? So 204, we're actually working with the linked list structure. Okay, the other ODPs, we just had an array of struct nodes. This one, we're assuming that the array of struct nodes that we're given is actually a linked list. And we're assuming throughout that element 0 is the sentinel node, so it's always present. And the next field of element 0 is therefore the index of the first data node. Okay, the data value at index 0 is not meaningful to us because it's a sentinel, it's not part of our data. But if there is a first node in the list, the next field of the sentinel will point to that node, point to it meaning it contains the index in the array of that node. If it's equal to my-null minus 1, that's telling you that there is no first data node. There's a sentinel and the list is empty other than the sentinel. All right, so your goal is to write this get first routine, and the prototype looks like this. So it takes in a linked list, okay, a struct node array, and it takes in a pointer to an integer which is called error. So you pass this with an ampersand in front of it, right? It's like when you call scanf and you want scanf to change the value of a variable. That's what we're doing. We're passing an integer, and our routine is going to load a value into that integer. Okay, but because C is passed by value, we have to pass the address, and it'll store its result in the thing that's pointing to. So your function returns an integer. Okay, the int in the beginning, the function value is an int, and it's either the data value of the first node, okay, or it's a 0. Yes, or it's a 0 if there is no first node, if the list is empty. Okay, so that's one thing it does, it returns an int. The other thing it does is it loads a value into this error variable. If there's a first data node, error should be equal to 0. If the list is empty, error is equal to 1. So a caller can pass this a linked list, a struct node array, and it should get back a data value of the first node, or it should know if the list is empty. It knows whether the list is empty by checking the error variable. If error is set, the list is empty. If error is 0, the list is not empty, and the return value is the first data value. Does that make sense, how you use this? So to test this, right, make yourself a linked list array. Make an array of these struct nodes. The first one's a sentinel, so set the next value to some index, and at that index, store a data value, set the valid flag to 1, and doesn't really matter what you do with the next value for that. And when you call this, it should give you back the data value of that node that you use as the first data node. Then make a struct node array, but set the sentinels next to be my-null minus 1 and call this. It should return a 0, and that error variable should be set to a 1. If those two cases are doing those two things, then your function should be correct. Go ahead and assess it. All right, so link it into the test bed as usual, and then go ahead and assess. So I tweak the assess, and you can put in as many files as you want when you assess. So assess, executable, and then one or more source code files. Okay, and those will all get put into your log file. All right, raise your hand if you get some sort of notification from Canvas when I post an assignment like this. Okay, so that does happen, right? And you can set it to do it timely instead of at the end of the day, right? Okay, good. So as I mentioned in an announcement over the weekend, I won't give you an assignment on a Saturday or Sunday that I expect you to turn in Sunday morning or Monday morning. Okay, so I'll leave weekends sacred like that. But Monday through Friday mornings, 8 to 9 o'clock, you can expect an ODP to pop up, more or less without warning. I'll usually tell you, but if we don't meet or if it's the other section, you should still be getting notified by Canvas. All right, so any non-ODP questions, any programming assignment 1 questions? We're going to go through algorithms today for doing the different pieces of PA1. But if you have questions up front, yes?
I'll say, it's like, I'm working on the add part.
Okay.
PA1, and I know you want to start it with the getNode function. Essentially, it's a find where there's a valid slot memory to put your new data, and you're passing it the new data to put it with. So I've got that part, but then how do I go about finding its like previous next value, or if there's like a next value after it?
Okay, we can start with that.
Cases that
So let's start with that, and let's do this with pictures first, and then move towards doing this with code. So let's look at what our linked list looks like. So we have a sentinel. And we have this linked collection of nodes. And I'm just going to throw some bogus values in here. So 10, 20, 30. So there's a list of 3 nodes. And let's say we want to insert uh, 25. Okay, first thing you're going to do is call your search function. Make sure 25 is not in there. Do this before you call getNode or anything else. Because if you call getNode and you don't end up storing a node, you're wasting some space. Right, so before you do anything else, call your search function on this list with the value you're trying to insert. See if it's already in there. If it is, you don't have to try to insert it again. You return some status. So you call search, 25 is not in here. Okay, so we want to insert it. Let me do this with the back of my pens first, and then we'll go through it with some variables. But here's the idea. We start off with a sentinel, and that points to another node. Okay, so this blue pen is always the previous node. This green is always the following node. And we're trying to find out, should we insert our number in between the blue pen and the green pen? Okay, so we look at the data value on the green, it's a 10. It's bigger than 25, so we want to insert after the green. So we need to move down the list, and we're going to do that in 2 steps. First, we're going to move the blue to point to where the green is, and now we're going to point the green to whatever this node is pointing to, which is the 20. And now we want to know, do we put our new node in between these 2? So check the 20, the value at the green. 25 is bigger than 20, so it goes to the right. So again, move our blue over to the green, move our green to what the 20 is pointing to, and repeat. So we're in a while loop here, right? So now we compare our 25 to the green's data value 30. 25 is smaller than 30, and this is the first time we found a node where 25 was smaller than its value. So we know 25 has to go in between here and here. Okay, if we're using variables instead of pens, we've got a variable that points to this node, we've got a variable that points to this node. Now it's pretty straightforward. To do our actual insert, we simply create a new node, load the data value. This thing's next value should be whatever the previous node's next value was. Previous was pointing right here, so we'll set this to point there. And then we change the previous node so that instead of pointing where it's pointing, it points to the node we just created, and we exit. And we're done, we've inserted. Okay, let's think about edge cases. Let's insert a 5. Yes?
If we get the command to insert and we are already occupying all of the indexes in an array, do you want us to return some function?
I'm not going to test that case, but yeah, the best thing to do would be to return some flag that says we're out of space or print a message or something.
Okay.
But I should have put that in the assignment and I didn't, so I'm not going to test the case where you run out of memory.
What situation would you hypothetically run out of memory?
In this case, if you're putting in more than 100 pieces of data, or more than 99 pieces of data actually, you're going to be out of space in your array because your array only has 100. In the PA2 context, if you use up all the memory on the system and you try to create a new node, there's no memory available, right? So your system is hosed. All right, so let's insert a 5. We're going to do exactly the same thing. So we're going to start with green pointing at the sentinel, blue pointing at the node that the sentinel points to, and we say, does the 5 go in between these? So we compare 5 to blue's data, which is 10, and the answer is yes, 5 is less than 10. We want to insert in between here. We do exactly the same thing we just did. We make our new node. We load the data value. We have it point wherever the previous node is pointing. The green node is pointing up here. So we set the next field accordingly. And then we change the green node's next field to point to our new node. And we exit. And it's the exact same algorithm, even though we're inserting in the beginning of the list. This is what the sentinel is doing for us. If it weren't for the sentinel being there, we would have a special case when we insert it in the beginning. But in this case, it's exactly the same. Okay, what about the last edge case? Let's insert at the very end. So here again, we're going to move these things forward in pairs. We get here, we compare 35 to 30, it's bigger. So now we set our green to point to the blue node. We set our blue node to be whatever the next node is, which is my null. Okay, so this is no longer an index in our array, this is a special my null value. And if we try to look at index my null's data value, we're going to get a seg fault. So at this point we need a special case, which says we've gone to the end of the list, we've gone to where the blue node is no longer pointing to a node, and we still haven't found a place to insert. That's an edge case. In this case, we have to insert after the green. It's not being sandwiched between two nodes, it's getting tacked onto the end of the list. So we'll create a new node. We'll set our data value. But instead of setting the next value to something else, right, we'll set it to my null, which is still what this previous node was pointing to. And we'll change this to point to our new node. So it's almost exactly the same set of steps. So how can we do this with something closer to programming instructions? Let's make a pair of pens. Okay, I'm going to call them previous and next. So I'm going to start off with integer previous, and that's going to be 0. And this is index of previous node. That's the index in this array of struct nodes. Our next node is going to be what? How do we find what node comes after the sentinel?
The next value of the first node.
Okay, so let's just assume that our array is called LL. So LL bracket previous dot next. I could have just done LL bracket 0, but we're going to generalize this. Okay, this is ODP 204, more or less. But don't try to just plug in 204's code here, right? 204 is doing a lot more than just this. But this is the essence of it. We're finding the first data node. And if this turns out to be my null, we've got to do something special. But let's ignore that for a moment. So let's write pseudocode. So what's the data value of the next node? What's an expression that'll get us the data value of the next node? Right, the node at index next. LL next dot data. Okay, that's this value of whatever the next node is. And if that's bigger than our data, so this is insert LL and our data. So if the next node's data is bigger than our data, we want to insert right before the next node, which means in between the previous node and the next node. So we want to insert right before here. Well, so we have to make a new node. So we can do something like temp right, get a node. Check it to make sure that it's not reporting my null, that you're out of space. So add some check to see if it's legal. Otherwise, here's what we have. So let's look at the case of 25. This will be previous. This will be next. And this will be temp. Okay, so we're going back to our pictures to help piece this out. So at this point, previous is the index of the prior node, next is the index of the subsequent node, temp is the index of the new node that we just created. So we got to do three things. We got to set the data value of temp to whatever our data is. So what does that look like in C? We want to set the data value of the node at index temp. LL temp dot data equals our data. So we set the data value. And then we wanted to have this new node, temp, point where the previous node was pointing. So I want to set our new node's next field equal to what? Exactly, LL previous dot next. Now our new node is pointing to the next node. And then what's the last thing we have to do?
Set previous next to temp.
Set the previous's next field to be temp. So that previous is pointing to temp. And we're done. We've inserted our node. So we can just return. Does that make sense? So make a box, have it point where the node before it is pointing, and then have the node before it point to it. That's the intuition, that's the behavior we're after. We got to understand that first. And then here's some things that look like C, but they're not really C, that describe how to do that in terms of this array of struct nodes. Right? And this is what we do if we want to insert a new node. But if we haven't found the place where we want to insert, what do we need to do? We need to take the previous and have it move over to where next is, and then have next move to the thing that next is pointing to. So outside of this loop, we're going to want to do the following. All right, so this is some kind of else statement. So have previous be the index of what was your next node, and have next take on the index of the node that comes after what was the next node. And we can loop until next equals my null. And if you keep doing this and you get all the way down here where next is equal to my null and you still haven't inserted, which means you haven't done your return, then you know you just need to make a new node, insert after next, and have next that point to it. So temp equals get node. Temp data equals our data. And then previous next equals our new node, and our new node next is my null, and return. So questions about this? As usual, right, this and this, worthless, right? Those things by themselves are not particularly valuable, right? What's most valuable so far is this idea of what the steps are that you need to take to do an insert. If you really understand those steps, the challenge is to understand how this corresponds to that array of struct nodes. And it's probably worth rehashing that. So let's imagine this. So there's our original list that we were starting with. Let's see what this might look like in memory. So here's LL. And LL, an array of struct nodes, means each entry has 3 fields: data, next, and valid. So there's an arbitrary example of what your LL array might look like. And we should be able to look at this and say, what is the linked list that we have stored in this LL array? Well, LL0 is always our sentinel, which means it has the index of the first data node. That index is 2, so this is the first data node. It's got a value of 10, it's valid, and it has a following node at index 4. At index 4, we have a node with a value of 20, that's this, it's valid, and it's followed by a node at index 3. At index 3, we have a valid node with a data value of 30, and a next field of myNull, which means that's the end of the list. So this set of data corresponds to this picture. And now if you want to go through the steps of, say, insert a 25, well, previous would start off at 0. Next would be whatever previous, LL previous dot next. Well, LL0 dot next is equal to 2, so next is equal to 2. Okay, so when I say previous is right here and next is here, what I actually mean is that previous is the index where this node is stored in our array. Next is the index where this node is stored in our array. And so when we check LL next dot data, we're checking entry 2's data value, that's a 10. And we see that that's not bigger than the number we're trying to insert, 25. So now we move down the list. And what do? We do two things. We say previous equals next, and we say next equals LL next dot data. Sorry, dot next. So when we do this, previous is set equal to the value of next, which is 2, and next is set equal to index 2's next value, which is 4. So these two lines of code have the effect of changing previous to 2 and next to 4. In other words, previous is the index in our array of this node, and next is the index in our array of this node. So we've moved down.
So it keeps updating the next data output, or the value of the next, right?
It doesn't touch the data, but it just updates these two indices into our array so that they're always pointing to two nodes between which we might want to insert our new number. And then if we get down here where we're looking at this node and this node and we want to insert in between, then we do those other steps.
What's this there? The last line there, next to next. Dot. Oh.
That's a scribble. All right, the order in which you do this can make a difference. So here's our previous. Here's our next. And here's our temp. All right, and we said the way we're going to insert this, we're going to have temp, so LL temp next equals LL previous next, and then LL temp, sorry, LL previous next equals temp. So this is creating this arrow, and this is doing this. And the order in which you do those is important. If I do this green thing first, I change my previous to point to temp. Now when I make my temp point where my previous is pointing, temp's going to point to itself. Right? So if I change the previous as next first, I lose track of where previous used to point. Right? And if I say point where previous is pointing, it's pointing to itself, it's circular. And now every time that you try to go down this list, your code's going to look like it's not doing anything, because it's just going to loop forever.
So, do you know if how do you break the compiler when it does that, if it keeps looping?
If it keeps looping forever, just hold down Control, press C. That interrupts your program. Yeah. Thanks.
Can you just set LLtemp.next equal to next and not have to worry about that?
Yes, in this case you could. Wait, say that again?
Can you just set LLtemp.next equal to next? Since LLpreve.next is next.
Yes, you could do that too. Yeah. Yeah, there's a reason I'm doing it like this, which doesn't make any sense yet, but yeah, that's the same thing.
So the way that he just described it would get around this, but it wouldn't get around other things that we'll see in the future?
Correct, yeah. All right, let's let that gel for a minute. Let me touch on something else. I had some questions about this this get node function that goes through. No, what was it? It was, I think it was release node. That you give it an index and it sets that entry's next field to my null, right? To basically mark that entry as being available again. And somebody asked me, why do we have to do that with a separate function? Why can't we just set it equal to -1 inside the delete code? Delete's the only place you're going to use this. Why can't we just set it equal to -1 instead of calling this release node function? It goes back to this idea of information hiding. So here's your main code, here's your delete code, here's your release node, or whatever it was called. Yeah, release node. What we're doing is one way of implementing a linked list with this array of struct nodes. And our struct node has 3 fields. It has data, it has next, and it has this valid flag. And next is the index of the next node unless you're at the end of the list, and then we set it equal to -1. Well, suppose memory is getting expensive and we're spending 3 integers every time we want to store one integer in our list. Suppose we say, you know what, I don't need a separate valid field. I'm going to have the next field take on another role. If I set next to -1000, that's going to mean valid equals 0. So next is usually the index of the next node. If it's -1, that's a flag saying we're at the end of the list. But if it's -1000, that means the node is not in use. Any reason I can't do that? You're the programmer, you can do whatever you want. And guess what? Now you're only using 2 integers instead of 3 for each piece of data. That's a good change. The issue is, inside your delete code, if you've got something that says set the valid field equal to 0, set the valid field equal to 1, you got to figure out where you did that. You got to change it accordingly. If you're calling release node, all you got to do is change the release node routine. And your initialization routine, all that's really got to do is create a sentinel node and then call release node for all the other nodes, and that'll set the valid flag to -1 or to 0. And if you change that strategy, if you change release node and you recompile, you don't have to change any other code. So there's this separation of functions, this layering, this hierarchy of who does what. These lower level routines, release node and get node, manage the low level manipulation of the struct node array. And eventually those are going to manage the low-level manipulation of memory itself. The delete, insert, search use those routines to do things for main. Main just gets user input, figures out what the user wants, and then calls these middle-level routines to do those things, right? And now if these middle-level routines change, we don't have to tinker with the code in main. As long as it's still called delete, right, main's going to look the same. So we're back to looking at this separation of layers and trying to segregate out functions. All right, back to boxes. So let's look at some simpler functions. So there's our list of 3 things. Let's look at a print routine. So print, I'm going to call it traverse. Traverse means go through your data structure in some order and typically print what you find. So let's write a traverse routine that moves through our list and prints out each data value. So again, we're going to start with what the Sentinel node is pointing to, and I'm only going to need one pointer this time. It's my blue pin. So I'm going to start off by pointing to this. I'm going to print out its data value, and then I'm going to move this variable to whatever this node is pointing to. So I'm going to look at its next field. That's what this is going to be pointing to now. I'm going to print out the data, change this to whatever the next field is pointing to, print out the data, change it to whatever the next field's pointing to, and I'm going to quit when my pen is no longer pointing to a node, but it's actually taken on the value of my null. At that point, I know I've gone through to the end of my list. So I can do something like this. So next equals LL0 dot next. So that's the first data node, or it could be my null if the list is totally empty. So while that's not my null, it means that next is pointing to the next node I want to print. So how do I do that? Well, just print LL next dot data. So that's the data value. And then I want to move down the list. I want to change next to be whatever next is pointing to. So again, next equals LL next dot next. And you're done. There's your whole print algorithm. And this is kind of the magic. All right, that's how we move down the list. We take whatever it's pointing to and we go to that node and we repeat. But if you can make sense out of this, you can do search. It's almost exactly the same thing. It's got one extra thing, which is instead of printing, we compare that data value to what it is we're looking for. And if it's equal, we can return right there and say I found it, right? And if we get all the way to the end of this while loop and we haven't returned, we didn't find it, and so we return a flag saying it's not in the list. So search is almost exactly like print. And then delete is a little easier than insert or add, right? Delete, we go through and we're still keeping previous and next, but when we find the node, we want to remove it, so we basically have the previous node point wherever the current node was pointing. And then we say release whatever that current node is.
Could we use return that thing instead of using print, like in sync. Is there a way to do that? Because when I tried to do it for the ODP, it didn't work out.
Returning what?
The like data, you know, this data in the node, yeah.
Yeah, you could return data instead of printing it. Sure. That's not going to help you with traversing the list.
Well, yeah.
But yeah, it's perfectly legal. Absolutely. But I don't think I looked at your code for the ODP, so I'm not sure what might have been going wrong. But you can come by office if you want to show me.
Is it after class?
I think I have office. Oh no, I don't. But you can come by anyway. You just have to watch me. Oh no, I can't. I have something I have to do at 12.
And this is just like a simple template to like iterate through the list.
Yeah,
if
yeah.
you wanted to find the location where
Yep.
the data could be done.
Exactly. Yeah. So this is the template for moving down the list, right? And you may not want to print. You may want to compare, or you may want to do something else. But it's the same thing as what we saw previously. I don't have it. But yeah, it's just following pointers. All right. Other questions, or should we eyeball delete? Let's look at deletion. You're never done drawing little pictures.
So now if you have any more shows to watch, you can just go home.
That's true. All right, so let's say we want to delete 30. Sorry, let's delete 20. We'll stay away from edge cases first. So same thing, we're going to start at the sentinel and the node after it, and we're going to see if we need to delete whatever the blue is pointing at. No, so we're going to move forward. Should we delete what the blue is pointing at? Yes. Okay, at this point, all we have to do is make a change to the previous node, have its next field point wherever blue's next field is pointing. So we'll change this to point over to the 30. So we can write something like, so let's call it previous equals 0, next equals LL previous dot next. And check to see if we should delete what that next node is. So if LL next dot data equals our data, then yes, we want to delete. So the previous node should point where the next node is pointing. So the previous node next should be equal to the next node next. And then release the next, so this node, and return. Otherwise, move down the list. We already know how to do that. And then just keep looping. So So previous and next. Next data field is 10. That's not the 20 we're looking for. Set previous equal to next. Set next to whatever next is pointing to. Next data is equal to 20. That is the data we want to delete. So we say LL previous next should be LL next. So the previous node's next should be the same as whatever the next node's next is. That causes this to point over here. And then we say release next, and that basically marks that as invalid, so now it's available. Next time we need a node, we can pick up that entry. And we've deleted the 20. And again, because of the sentinel, if we're trying to delete a 10, we're starting off, next is the sentinel, sorry, previous is the sentinel, next is the 10. First time through, we decide we want to delete this, we simply change the sentinel to point wherever this is pointing. It's going to point to the node that comes after 10. No edge cases.
So after a whole bunch of like additions and deletions, you like after a deletion, for instance, would you want us to remove the actual node or just leave it where it is and just have it bypass?
What does it mean to remove it?
Like remove that data from memory, or is it just left there and then the node bypasses that specific value?
How would we remove it from memory?
I don't know.
It's a good question.
Isn't that what release node is for?
So that's what release node is pretending to do,
Okay.
right? Because we have an array of 100 struct nodes, they're always in that memory, right? We can't somehow give that up. But by setting the valid flag to 0, we're effectively saying this is available again for other uses. Now in PA2, instead of calling getNode, we're going to call malloc. And malloc is going to talk to the operating system, and the operating system is going to hand us a block of memory and say, here you go, this is yours, right? And that's going to be where we store our data and our new next field. And when we're done using that, we're going to call a routine called free. And free is an operating system interaction that says, okay, take this block of memory, put it back in the pool of memory that's available, what's called the heap. And then next time you need a block or somebody else needs a block of memory, they might get that block. So getNode and release node are our versions of malloc and free. And with PA2 on, we'll be doing malloc and free every time that we work with data structures. Good questions.
So that's what that guy you said was using it for.
Say again?
Or the substitution. He did that with the release node.
Yeah.
And it worked.
Yeah, and this kind of thing where we're indexing an entry in an array, right, that only works because we're using an array to store our memory. The syntax for that's going to change when we're actually working with pointers into memory. And we'll go over that probably starting tomorrow. Yeah.
Would deleting like all of the invalid nodes and then truncating the array be part of like compression?
You could do something like that. You could try to periodically go through your array and move it into the beginning of your array. Generally, we don't do that, but I could see a case where your memory got really fragmented and you want to bring it all together to be located close to each other. And yeah, you could do exactly that. And that could be an efficiency help. All right, cool. So work on your ODP. I don't know if I'm going to post a 205 tomorrow or not, because at this point I kind of want you to be able to work on your PA. So we may just run with that. Or I may start some ODPs related to what's coming next. So tomorrow we'll probably start looking at what PA2 is going to involve. All right, I will see you tomorrow.